Hello and welcome to lecture 14 of our course on stochastic modeling of biological processes. In sections 4.1 and 4.2, we presented two models of diffusion, which were simple examples of position jump processes. Such processes can be characterized by abrupt changes in the position of diffusing particles at random instants of time. In particular, it does not make sense to talk about particle velocities for position jump processes. If we formally define the velocity as the derivative of the position by this formula, then such a derivative would be infinite whenever a position jump occurs instantaneously and zero when a position jump doesn't occur. In section 4.3, we present two models for diffusion based on so-called velocity jump processes. For such processes, the particle position xt evolves according to this equation or its discretized version, which is written with the help of the finite time step delta t, and the particle velocity vt is subject to a stochastic process. I should note here that vt denotes the velocity in this lecture, and later in chapter 8 when we discuss microscopic modeling of Brownian motion. In particular, we will not use v to denote variances as we did in some previous lectures. The presented velocity jump processes will provide another possible way to describe the diffusion process. In particular, they can again be used to implement our illustrative diffusion example visualized in this video, which we have already calculated in two different ways in sections 4.1 and 4.2. Our illustrative example describes diffusion in one spatial dimension. Therefore, without loss of generality, we will also introduce velocity jump processes in one spatial dimension. The diffusing particle will move along the real axis. In our first velocity jump process, the velocity of the particle will only take two values, positive and negative s, where s is the speed of a diffusing particle. Thus, the particle moves along the x-axis at a constant speed s and reverses its direction at random instants of time. The probability of turning in the infinitesimally small time interval t plus dt is equal to lambda times dt, where the turning frequency lambda is given by this formula. In particular, our velocity jump process is characterized by two parameters, the diffusion constant d and the speed s, with the third parameter lambda calculated by this formula. Having introduced our velocity jump process using an infinitesimally small time step dt, we can immediately design a stochastic simulation algorithm to simulate it by replacing dt with a finite small time step delta t. The algorithm is given as the SSA A10C10 on page 108. First, we generate a random number r uniformly distributed in interval 0, 1. Then we update the position and velocity of the diffusing particle. The position is updated using the forward Euler discretization of the derivative of x, given in equation 435. To update the velocity, we compare the random number r with the probability of turn, which is equal to lambda times delta t. If the turn occurs, then we reverse the velocity. Otherwise, the velocity is kept the same in the next time. This algorithm correctly implements our velocity jump process, provided that the probability lambda times delta t is significantly less than 1. That is, the probability of two turns happening during one time step is negligible. So this gives us a restriction on the size of the time step. The derivation of the SSA A10C10 is analogous to the derivation of the naive stochastic simulation algorithm of degradation from section 1.1. We substituted the infinitesimally small time step dt by the small finite time step delta t to get these algorithms. In section 1.1, we were able to replace the naive stochastic simulation algorithm by the Gillespie algorithm, which was less computationally intensive. The key point of this event-based algorithm was the derivation of an equation which specifies the time when the next event occurs. The SSA A10-C10 can be improved in a similar way. Instead of using many random numbers between successive turns of the diffusing particle in the step C10, we can calculate the time of the next turn directly using only one random number. The resulting event-based algorithm is presented as the stochastic simulation algorithm A11C11 on page 111. The time of the next turn of the particle is calculated as t plus tau, where tau is an exponentially distributed random number which can be obtained from the uniformly distributed random number r by using this formula. The same formula has been previously used in the Gillespie algorithm. Once we know the time of the next turn, we know that the velocity will not change until time t plus tau. So we can update the position until that time, and we change the sign of the velocity at time t plus tau. In figure 4.4, we present 6 illustrative trajectories calculated by both algorithms. The left panel is calculated by the SSA A10-C10, which uses the finite time step delta t, and the right panel is the event-based algorithm A11C11. Each realization was started at point x0 is equal to 0, and the initial direction was chosen randomly. As expected, there is no observable difference between the computed illustrative trajectories. To use these algorithms, we need to specify the values of diffusion constant d, speed s, and turning frequency lambda. The diffusion constant d can be considered to be given in our examples, because we have used the same value of d as in our previous lectures, the value of d which is relevant to diffusing proteins. The turning rate lambda in this model is fully determined by the speed s and the diffusion constant d using this formula. Therefore, we only have to think how we can reasonably specify the speed s. In section 7.3, we will use velocity jump processes for modeling behavior of unicellular organisms, like bacteria, where their turning frequency lambda will be around 1 per second. If particles are unicellular organisms, then we can use such experimentally measured values. What about if we want to apply our velocity jump process to the simulation of a diffusing protein molecule considered in our last lecture? What are the appropriate values of diffusion constant d, speed s, and turning frequency lambda? These two plots were calculated for such values, and you might have noticed that the units on the time axis are nanoseconds and the units on the space axis are nanometers. And there is a good reason for such small values. In our simulations, we use the diffusion constant of a typical protein molecule as 10 to minus 4 mm square per second. The same value was also used in our illustrative simulations of position jump processes. To estimate the speed s, we will use a simple result from statistical physics, relating the kinetic energy to the temperature. Here T is the absolute temperature and Kb is the Boltzmann constant. The kinetic energy is mass times speed squared divided by 2, and this is equal to kBt over 2. Solving for s, we obtain that we can estimate the speed as the square root of kBt divided by the mass of the protein. On the right hand side we have the Boltzmann constant, the absolute temperature, and the mass of protein. Using the temperature of human body as 310 Kelvin and molecular mass 25 kilodalton, we can estimate the speed s as 10 meters per second. That is a relatively very large speed, which could on the face of it be a little surprising to some of you. In 1 second, the protein will fly across the room of size 10 meters. If my lectures were delivered in person, I would demonstrate this by throwing a plastic model of a protein across the lecture room. One advantage of remote learning is that you are not subject to such flamboyant demonstrations. Obviously, no real protein will fly straight for 10 meters. They do have to move randomly with the right diffusion constant d. In this simple velocity jump process, this is achieved by choosing the turning frequency lambda according to this formula. Substituting 10 meters per second for speed s and using this diffusion constant, we estimate lambda to be 5 times 10 to the power 11 per second. That is 500 turns per 1 nanosecond, which explains the physical units on the axis of figures 44a and 44b, which I showed on my previous slide. This also restricts the size of our time step delta t in figure 44a. In that simulation, I had to make sure that lambda times delta t is significantly less than 1, so I chose delta t to be 20 femtoseconds. This is not the smallest time step you will find in the lecture notes. In Chapter 8, we will consider more detailed models described in terms of molecular dynamics simulations, where we will simulate positions and velocities of individual atoms. And the price which we will pay for using such a level of detail will be that we will have to use even smaller time step, equal to 1 femtosecond. Having explained how we can simulate and parameterize the velocity jump process, we will now turn our attention into its analysis. As in our previous examples of stochastic simulation algorithms, we will analyze it by writing suitable evolution equations for probabilities. Since particles are non-interacting, these equations can also be interpreted as equations for densities of particles. We denote by P plus xt the density of particles that are at point x at time t and are moving to the right, and by P minus xt the density of particles that are at point x at time t and are moving to the left. On page 112 of the lecture notes, I presented the derivation of equation 440 for P plus, and I left the derivation of the analogical equation for P minus to you as exercise 4.5. You could try to derive both equations 440 and 441 yourself. However, if you have any difficulties with this derivation, then please first read the derivation of equation 440 in the lecture notes, and then modify this derivation to solve exercise 4.5 by deriving equation 441. Equations 440 and 441 provide an equivalent description of the velocity jump process. We are interested in the equation for total density P, which is defined as the sum of P plus P minus. It gives us the density of particles at point x at time t. To derive the equation for P, we add and subtract equations 440 and 441. If we add them together, then the resulting equation will include a time derivative of P. If we subtract them, then the resulting equation will include the partial derivative of P with respect to x. By cross-differentiating these equations, we obtain that this system of first-order equations for P plus and P minus is equivalent to one second-order equation for P, given as the so-called Telegraph Equation or the damped wave equation, which is equation 446 in the lecture notes. Considering sufficiently long times, which are much greater than 1 over 2 lambda, we can neglect this blue term and derive the diffusion equation in this form. In particular, the diffusion constant is s squared divided by 2 lambda. Solving for lambda, we obtain formula for 34, which we have used in our simulations. Since we have derived the diffusion equation, we have also justified that our velocity jump process provides another description of diffusion. Here, I would like to note that the equation 446 is exact, while the diffusion equation 447 is only an approximation that can be justified for times which are sufficiently larger than this coefficient 1 over 2 lambda. In fact, we could expect such a result for this stochastic process. We do have an extra parameter to choose, speed s, and an extra initial condition for the initial velocity. If the duration of the observed time interval is much shorter than a typical time needed for one turn, then the particle just goes straight during this time interval, and the initial condition for the velocity determines the initial direction of the particle. However, after a few changes of the velocity, the initial condition for velocity is completely forgotten by the system. So for times much greater than 1 over 2 lambda, the behavior effectively only depends on the initial condition for the position, and it is described by the diffusion equation on that time scale. Since this velocity jump process describes diffusion, we can also use it to simulate the illustrative example from sections 4.1 and 4.2, where we considered the time evolution of the x-coordinates of molecules diffusing in the interval 0L. To use the velocity jump process, we have to apply the same reflective boundary conditions at both endpoints, x is equal 0 and x is equal L. The resulting stochastic simulation algorithm can be found as the SSA A12D12 on page 114. The first two steps, A12 and B12, are identical to the steps A10 and B10 of our previous velocity jump process algorithm. We generate a random number R uniformly distributed in interval 0, 1 in the first step, and we compute the position of the particle at time t plus delta t in the second step. If this formula leads to the position xt plus delta t, which would be outside of our computational domain, outside of interval 0L, we reflect it back to the interval 0L in the step C12. That is, if xt plus delta t is negative, then we change it to a positive value and we change the direction of the velocity as well. Similar reflective boundary conditions are implemented at the right boundary in the step C12. Finally, the last step, D12, uses the random number R to simulate the random changes of the velocity. This step is again the same as in our previous implementation of the velocity jump process. In summary, the only new step is the step C12, which implements the reflective boundary conditions. The results obtained by this algorithm are presented in figure 4.4c, where we have calculated 10 illustrative realizations starting at the point x0 is 0.4 millimeters. The simulation of 1000 molecules is visualized in figure 4.4d, exactly in the same way as we did for the position jump processes in sections 4.1 and 4.2. To get such a comparable plot, we have used the same value of the diffusion constant d in all simulations, which was chosen to be a typical value of the diffusion constant for proteins. Considering the velocity jump process, we also have to specify the value of the speed s. We have previously estimated that the speed s for diffusing proteins is about 10 meters per second, which resulted in a relatively large turning frequency, equal to 500 turns per nanosecond on average. To obtain these plots, I chose s much smaller than that, equal to 10 micrometers per second. So S was smaller by the factor of 1 million. Consequently, the turning frequency lambda was also smaller by the factor of 1 million. So we only have, on average, one turn every 2 seconds. In particular, my simulation was 1 million times quicker, and I could efficiently simulate the system over several minutes. Looking at these figures, we confirm that we have developed an equivalent description of our diffusion example using a velocity jump process. So we now have three models of diffusion, two position jump processes and one velocity jump process. Next, we will introduce another velocity jump process, which could also be used to simulate this example. Such a figure is not presented in the lecture notes, but you could try to calculate it yourself. Our second velocity jump process is given by equations 449 and 450, where d is again the diffusion constant, beta is another parameter called the friction coefficient, and psi is normally distributed random number with zero mean and unit variance. We observe that the equation for the velocity is a stochastic differential equation. So in this example, velocity v can take any real value. This velocity jump process can be formally rewritten for a particle with mass mp as Newton's second law of motion. The derivative of the position is equal to the velocity, and the mass times the derivative of velocity is equal to the applied force, where there are two forces on the right hand side, a frictional force and a random force. The frictional force is proportional to the negative of the velocity, where coefficient gamma is equal to mass mp times beta. This is a very standard description of friction. The random force is a heuristic, because we know that we cannot differentiate the Brownian motion. In fact, the limit of the time step delta t goes to zero, which we have used to formally obtain these differential equations, does not make sense even from the physics point of view. This model replaces the interactions of the diffusing particle with its environment by a random force. If we explicitly modeled the environment, it will be made from other molecules, and the force on the diffusing particle will be the result of interactions with the surrounding molecules. In particular, if we consider two time points, T1 and T2, which are very close to each other, then the environment did not change much, and we would expect that the force at time t1 is very similar to force at time t2. However, our normally distributed random forces assume that the force terms are not correlated between the time steps. Equation 450 states that the random force at time t plus delta t could point in an opposite direction than the random force at time t. A more realistic description will be written in terms of the generalized Langevin equation in section 8.2. However, in this lecture, we will not worry about this. We will simply postulate our velocity jump process in this form, 449 and 450. And we will discuss its properties. First, we divide equation 450 by beta and pass to the limit beta goes to infinity. Then these two terms disappear, and we have that Vt delta t is this random term. Substituting into equation 449, we obtain the SDE-based model of diffusion 411. So this was a very quick way to justify that we again have a good model for diffusion with diffusion constant d for sufficiently large beta, or equivalently for sufficiently large times t, as we have already observed with our first velocity jump process. Here, let me note that we could also analyze this velocity jump process by writing an equivalent Fokker-Planck equation for the corresponding density function and passing to the limit beta goes to infinity. Such an approach is presented in the lecture notes on pages 115 to 117. We again obtain the diffusion equation with the diffusion constant d. The velocity jump process 449-450 can also be analyzed in the limit delta t goes to 0, in the same way as we analyze stochastic differential equations in chapter 3. For example, consider the initial condition v at time 0 is equal to v0, and let us find the first moment vt as a function of time t, initial velocity v0, diffusion constant d, and friction coefficient beta. Let us note that in this lecture, this symbol denotes the average over many realizations of the velocity jump process. We can use two approaches to find the average velocity v at time t. First, we note that our discretized formulation of the velocity jump process 449-450 gives us the value of the velocity v at integer multiples of the time step delta t. So let us consider that time t is equal to n times delta t, where n is an integer. Taking averages of both sides of equation 450, we obtain that the average velocity at time t plus delta t is equal to the average of the right-hand side. Since xi is the normally distributed random variable with zero mean, we obtain that the average right-hand side is just a constant multiple of the average of the velocity v at time t. Therefore, the average velocity v at time t is this constant, 1 minus beta delta t to the power n, multiplied by the initial condition v0. Passing to the limit delta t goes to 0, we get that vt is v0 times exponential minus beta t. In summary, in this first approach, we first exactly solved the discretized problem, and then we pass to the limit delta t goes to 0. However, we do not need to solve the discretized problem. In our second approach, we first derive an ordinary differential equation for the moment of interest, which we can solve to obtain the same answer. Taking averages of both sides of equation 450 and rearranging, we obtain this formula. Next, we pass to the limit delta t goes to 0 to obtain this ordinary differential equation. Solving this ODE with initial condition that v at time 0 is equal to v0, we obtain the same result as before. As an exercise, you could calculate other moments as well. For example, the second or third moments of velocity, or even the second moment of position, or the correlation between the velocity at time t and at later time t plus tau can be calculated by using approaches which we learned in chapter 3 when we discussed stochastic differential equations. Finally, I will conclude this lecture with one application of such results. I will discuss the Einstein-Smoluchowski relation, which is presented in section 4.6. In the lecture notes on pages 130 to 132, you can find one possible derivation of this relation. So let me present here an alternative derivation. We can use the technique from our previous slide to obtain that the second moment of velocity is equal to beta d plus a constant multiplied by exponential minus 2 beta t. Passing to the limit on the right hand side, the second term goes to 0. So you will obtain that for very large times, the second moment of the velocity is approximately equal to beta d. Therefore, the kinetic energy associated with the movement of a particle of mass mp along the x-axis is equal to kbt divided by 2, and substituting for the second moment of velocity into this formula for the kinetic energy, I obtain that this is equal to mp beta d divided by 2. Solving for d, we obtain the Einstein-Smoluchowski relation, that the diffusion constant d is equal to kbt divided by gamma where gamma is the frictional drag coefficient. The Einstein-Smolchowski relation can be used to estimate the value of the diffusion constant d. To estimate the value of the frictional drag coefficient, we consider a sphere of radius r diffusing in incompressible viscous liquid. Then the frictional drag coefficient gamma is equal to 6 pi eta r. Substituting this formula into the Einstein-Smolchowski relation, we obtain the Stokes-Einstein relation, that the diffusion constant d is kBt divided by 6 pi eta r. If we approximate a protein molecule as a sphere of radius 2 nanometers in water at room temperature, then the Stokes-Einstein relation gives us that the diffusion constant d is 10 to minus 4 mm square per second, which is the value we have used in all examples presented in lectures 12, 13 and 14. This brings me to the end of lecture 14, where we have presented two velocity jump processes from section 4.3 and the Einstein-Smolchowski relation from section 4.6. Please read pages 108 to 117 covering section 4.3 and pages 131 to 132 covering section 4.6 of the lecture notes before watching the video of lecture 15. In our next lecture, we will finish our discussion of chapter 4 covering diffusion to adsorbing surfaces and boundary conditions for diffusion. Thank you very much for listening to lecture 14 of our course on stochastic modeling of biological processes. Bye bye.